Greetings everyone. I welcome you all to this video discussion of the relationship of torque and angular momentum prepared by us, the group 2 from grade 12, Queen of Confessor. A quick breakdown of how we're going to tackle this lesson. We have three center of attention. First of all, the torque, and second one is all about the angular momentum, and lastly, the relationship of the two. I'll carefully explain its definition, provide an example, and show its application in real life in order to prove its necessity in our learning. Now, we have torque. Torque is the measure of force that can cause an object to rotate about an axis. It is simply what causes an object to acquire angular acceleration. It is a measurement of the force which causes something to rotate around a point. Torque makes things rotate faster or slower depends depends on the length of the object. The longer the length, the easier it is to produce torque. Remember that. Now the formula for it is the applied force times the distance over which the force is applied times sine theta. Now let's go ahead and have an example. Juggernaut will apply a 50 Newton of force on a 3-meter handle to open the lion cage, considering the force is applied perpendicular to the handle. Given is force equals to 50 newtons, the radius equals to 3 meters handle, the 3-meter handle, and the theta is 90 degree because it's perpendicular. Now obviously we're looking for the torque. And once again, the formula for it is the torque equals to F times R times sine theta. Now let's go ahead and substitute this. We have 50 Newton times 3 meters times sine 90 degree, which is equivalent to 1. Once we multiply this, we will have 150 Newton meters. Now, to further learn its concept, I'll be making one example. Now imagine this line is a wrench, specifically a 3-meter wrench. Here we have this. A shorter object like this will make it hard for us to rotate this, because if you put a force of 50 Newton multiplied by its radius, will only end up with 150 Newton per Newton meters. Now, compared to a longer object, which is the 5-meter wrench, we will be able to easily rotate this with the same force applied, because we will end up with 50 times 5 is equals to 250 Newton meters. So in conclusion, just like I've said earlier, the longer the object's length is, the easier it is to produce torque. Now let's go back to the presentation. Here are some of the example of its application in real life. The low and high gear of a bicycle and a car is due to the torque. Low gear provides low speed but high torque. High gear provides high speed but low torque. Also, simply enough, door can be used as an example if you consider the hinges as the axis of rotation. Now we have the angular momentum. Angular momentum refers to the vector quantity describing an object in circular motion. It is the momentum experienced by a rotating object. The quantity of rotation of a body, which is the product of its moment of inertia and its angular velocity. Momentum and angular momentum are both conserved. In physics, the term conservation refers to something which doesn't change. It just circles around its axis. Now, its formula is L is equals to m times v times r, or the moment of inertia times the angular velocity. Now we have an example of the angular momentum. I start pushing a merry-go-round with a torque of 10 Newton meters. It has a moment of inertia of 100 kilogram meter squared and an angular velocity of 30 radian per seconds. What is its angular momentum after 3 seconds? Now the given, we don't exactly need the torque for this solution because it's not actually needed in our formula, and we're looking for the angular momentum. Once again, its formula is the moment of inertia times the angular velocity. Now let's go ahead and substitute this. We'll have 100 kilogram meter squared times 30 radian per second. And our answer, multiply that, will end up with 3000 kilogram point meters meter squared per seconds. Here is our angular momentum. Now, let's go ahead and have an application. Our example is this helicopter. By using a tail rotor here, the helicopters are able to prevent their bodies from spinning out of control. Torque and angular momentum relationship. The torque is defined as the rate of change of angular momentum, which is the same as the cross product of the linear force and the distance from the axis. So the torque is the rate of change of angular momentum. Now that torque and angular momentum is in the same equation, the torque is being considered as the rate of change of angular momentum. Here is the formula. T is equals to delta L over delta T, wherein is the change in angular momentum, also known as torque. L is the angular momentum, and T is the change in time. Now, in order for us to be familiarized with this formula, our teacher provided us a very, very helpful pyramid formula, which is, as a matter of fact, very easy to use. All you need is to find, all you need is to cover up what you want to find. If you want to look for the angular momentum, cover it up, and there we have it. Torque times time, and cover time. If you want to look for it, we have angular momentum over torque. And if you want torque, all you have to do is cover it, and we have angular momentum and angular momentum over time. Now let's go ahead and solve this problem specifically made for us. A Lazy Susan food tray with a diameter of 73 cm is being rotated by a person in picking food. Suppose the person exerts a perpendicular force of 0.39 Newton to the Lazy Susan for 0.10 minutes. A. Find its torque in Newton meters. B. What is the angular momentum of the Lazy Susan in kilogram point meter squared over seconds per seconds if it starts from rest, assuming friction is negligible. Given the force is equals to 0.39 Newton and the radius is equals to 73 centimeter, but we need meters for the torque, so we need to convert it. All you need to do is just move the decimal point. But for a more credible source, we have a screenshot from Google, a converter, 73 centimeter is equals to 0.73 meter. And the sine is 90, the sine 90 degrees is from this perpendicular force. And the time is just like the radius, we need to convert it to minute to minutes from to minutes to seconds from minutes. So the 0.10 minute will become 6 seconds. And what we're looking for is the angular momentum. A formula from a identical problem such as this in Miss in our teacher's PowerPoint shows this specific formula, so we will use it as well. Now we need to substitute. The force is 0.39 times 0.73 meter times 1. This is the from sine, and 6 is the second the time. Multiply that, will end up with 1.7082. The final answer will be 1.7082 kilogram point meter squared per seconds. So that's how you answer. You just have to take note of the unit and follow the formula, and that's how easy it is to solve a problem such as this. So thank you for your time. Thank you very much for watching, and we hope sincerely that you've gained a good amount of knowledge from this video. Thank you so much.